This is circular motion for A levels. Okay, so the first topic he says that define radian in terms of angular displacement in radians. So we need to understand what is radians and degrees. So primarily from O levels and from very young age, we have been accustomed to the degree system, that a circle has 360 degrees. But we have a new unit in terms of radians that actually links the arc length, which is this one, with the radius itself. And the angle, because of these situations or because of these lengths, comes out as theta equals to S divided by R. S is the arc length and R is the radius. So when you take R to the other side, this is the formula that we get, that arc length is equal to radius multiplied by the theta. But notice that this theta is not in degrees, it is in radians, right? Now, what is a radian? How is it defined? So 1 radian technically is an angle subtended at the center. This is the angle. Under special circumstances, what is a special circumstance? That when the arc length is equal to the radius length or the length of the radius. For example, if the arc length is 15 centimeters, then the radius is also supposed to be 15 centimeters. Be that 20 meters, if the radius is also 20 meters, then this is what 1 radian angle will look like. Now, when you do all of these calculations, we come down to this conclusion that 1 radian under all circumstances, when you make sure that the arc length is equal to the radius, this angle actually comes down to 57.3 degrees. You don't have to memorize this. I'm just mentioning this as a state of fact, right? So from this point onwards, we realize that the complete radian or the complete the cycle of this system actually comes down to 2 pi, right? And 2 pi then represents 360 degrees and pi becomes equal to 180 degrees. But this is the unit of measurement or the unit of conversion that we use between the radians and degrees to convert them with one another. So we understand what are radians and what are degrees, and we understand this formula as well. Then we have concept of angular speed. Now this is new. Topic number 2 is new. Angular speed, as the name suggests, only tells us how much angle is being swept. So basically, angular speed is represented as the sign omega, which is a W, equals to the angle swept or covered divided by the time taken for that angle to be covered. Now, if we go back to O levels, for example, or even to young or smaller grades, we realize that this could be degrees per second, but we don't work with degrees anymore. We're going to work with radians. So the angle or the unit of this quantity comes out as radians per second. So how many radians are being covered with respect to time? So this becomes angular speed, which is represented as omega. So omega is equal to theta divided by t, or change in theta divided by time taken for the process. Again, theta will be in radians. We are not working with degrees anymore. Then we move on to the next part, which is understanding or recalling these formulas. So we understand that during a circular motion, if this is the direction of motion or if this is the direction of rotation, then there are 2 components available here. First is the centripetal acceleration, that is towards the center because of the centripetal force. Now we've understood a new quantity, which is the angular speed, represented as omega. But we also understand from O levels that there is always a tangential speed or a velocity that makes an angle of 90 degrees with the respective position. That usually was called tangential velocity, but since it is the only velocity present in a circular motion, we have removed the word tangential and we just know this by velocity v. Now, this tangential velocity and omega are linked by an equation which goes something like this, that v is equal to r omega. This is also one of the important equations. And then we have, for a complete rotation, omega equals to 2 pi by t. If there is a complete rotation, of course, then 360 degrees will be covered, and we know that 360 is equal to 2 pi. So we get these formulas from there. So 2 pi by t for a complete rotation, v equals to r omega, that link tangential velocity and the angular velocity over here. So working with this equation, there is a question in P4 that sometimes is asked from the students. I'm going to discuss that. Now, for example, there are at different radiuses. Let's say there is a mass m1, and at a different radius, let's say at the border, we have a mass m2. If the disk is rotating at a constant velocity or a constant angular speed, that means that this angular speed omega is going to be same for this m1 and for m2 because they're existing on the same disk. They're rotating with the same angular speed, right? So when omega is constant, we come down to the equation that V is proportional to R. What does this mean? It means that if you change the radius or if you change the distance of that object from the center, its tangential velocity will change. And that is quite evident from the system as well. We can see that for m1, the radius is smaller. So its tangential velocity will be lower. It will be moving with a smaller velocity. For m2, the radius is much larger. So when the radius increases, the velocity increases. Please be advised that we are discussing this in terms of omega or while omega is constant, because the disk is rotating like this. We understand that omega for the whole system is constant, right? So since it's placed further away, its tangential velocity will be much higher than the tangential velocity of this one. And it can be visualized from this system as well, that if an object was connected at the center at the same position, for example, let's say that on the same line of action, let's say that this was the mass that has to move over here, and we had a mass much closer to the center of the circle that has to move here. Now we understand that to exist at this location, object, let's say m1 and m2, m1 would have to move slower because it has a smaller distance to cover or a smaller arc length to cover. m2 would have to move faster because it has to go longer distance or it has to cover a larger arc length to exist at the same point, subtending the same angle as m1. So it has to move faster to get there in time or match the time of m1, right? So that is why this equation actually, this is what the equation actually telling us, that if you are away from the center of the circle, you'll have to move faster if the omega is constant, and usually it is constant for a system. Okay, moving on, we have centripetal acceleration, right? So the first point, he says there is a constant, and this is from O-levels. This is primarily from O-levels. We understand that a force towards the center of the circle is exerted, which is known as centripetal force. That centripetal force causes a centripetal acceleration, and from Newton's second law, we can say that centripetal force is equal to MAC, AC representing centripetal acceleration. Now, there used to be a proof for this, but that's not present in the course anymore. So you just have to memorize the formulas. And there are a few variables that we just need to remember. So centripetal force and centripetal acceleration are in the same direction. And velocity vector will be making an angle of 90 degrees with the force and with the acceleration. And there is a radius given in the question, right? Okay. So moving on from this point. So we realize that this is the centripetal force from Newton's second law. So we understand point number one, we have constant angular speed, understand centripetal acceleration causes, yes, we understand that acceleration causes the circular motion, and this acceleration comes from the centripetal force acting towards the center. So then we go towards the formula, or there are 2 to 3 formulas mentioned over here. Let's see how they are formulated. So we understand that V equals to R omega as done in the previous part. We know that the acceleration is equal to V square over R, and acceleration is equal to R omega square. These are the 2 formulas that we have. And from the Newton's second law, if you put in these formulas independently, this becomes F equals to MA and F equals to MA. If you put these acceleration formulas over here, this becomes mv square over R, and this becomes F equals to mr omega square, right? And you can interchange between these 2 formulas by replacing the R omega into these equations, and you will get the other one if you do that, right? So we know how these equations are formulated, right? We understand where the tangential velocity is, we understand where the angular speed is, we understand where the radius is, centripetal acceleration, and where the force is going to exist. So these are where the variables are going to exist in the diagram itself, right? So we understand this part as well. Now we're going to discuss where are we going to encounter them, or where do we encounter these cases, and how do we think about them. You might have seen that a car may make a turn, for example. A car may make a turn, let's say the car is moving in over here, it makes a turn to go towards this side. So from this point onwards, until the car finishes making a turn, there will be a centripetal force towards the center of the circle. And for a car to be able to do this, there will be a frictional force between the tires and the road that is going to make sure that this happens. But what happens, according to the centripetal force formula, this is F equals to mv square over r. Now, we understand that the friction between the tires and the road basically comes from the formula of a normal reaction, that from maths, mechanics, we know that this is actually equal to mu r, right? This is actually equal to mu r, the friction. But we're going to ignore the fact of the surface condition, and we're just going to consider that the centripetal force is being provided by the friction. Now, notice that if you were moving faster, let's say, then the friction required to do this job will be greater. If your mass of the car was greater, let's say you're in a truck or in a lorry, the force required by friction to do this job or successfully making the turn will be much higher. If you want to make a tighter turn, for example, you want to turn sharply, that means that the eventual or the imaginary radius of that circle will be lower, again requiring for a higher friction. That's why sports cars have bigger and better tires, because this is what they're trying to do, because this is what you are trying to achieve or demand from the sports car, right? Now, if in that situation, in that particular case, the road conditions do not allow for that, there is water on the road, or you suspect that the speed of the cars will be so high that no amount of tire can do this, then you will allow, or you will make banks on the road. So you might have seen these banked roads in movies, in shows, or probably in some documentaries. How do the banks help with this case? Now, first we need to draw the vector components, right? So we understand that this is the mg, or the weight component. According to this angle theta, this will be our normal reaction component, right? That goes exactly upwards. So this is going to be the mg cos theta, and this component will be mg sin theta. And this theta is copied over here according to the vector triangle rule, right? So not only that there is friction between the roads and the tires, but there will be a component of weight helping this circular motion if the car wants to make a turn over there to do this job. Now, notice that previously only the friction was responsible for the centripetal force. Now, friction is being helped by the component of weight, because they're both in the same direction. The friction is also in the same direction. By the way, friction is towards the center of the circle, because friction is responsible for centripetal force. The centripetal force has to come due to friction. That's why they're in the same direction. But now, not only friction is helping this between the tires and the road, but we have a component of weight as well, which is going to become equal to mv square over r. For those who are taking maths, mechanics, you will realize that this friction actually comes from mu r, or mu n, the normal reaction component, right? Over here, we can see that the normal reaction component actually looks like this mg cos theta. So this is mg cos theta. Depending upon the road conditions, if it is rough or slippery, the value of mu changes from 1 to 0. Right? So if it is a very if it's a very rough road with high friction, the value of mu is greater. If it is a very slippery road, the value of mu is less. So in place of friction, I understand that I have to replace the mu r, the normal reaction, plus mg sin theta equals to mv square over r. If you put in the normal reaction component, then this becomes mu into mg cos theta plus mg sin theta equals to mv square over r. I've done this for mathematics students, right? This is for the mathematics mechanics 1 students. But if you were just limiting yourself to A levels, then this would be your final answer. This is without the bank, this is no banking, and this is with the bank. That's why you notice that when the cars in shows or videos go for a high speed run, if they have to make a turn, the roads are generally backed, because they know that the friction might not be good enough. So they add the component of weight to help the circular motion, to help them make a turn so that they can maintain a higher speed in order to do so. Next, we have the rope and the ceiling stone mass case. We understand that this is actually rotating, right? The system is rotating like this. So what are the free body diagram vector components in this case? So let's consider this to be tension T. Let's consider this angle to be theta, and let's make sure that it is rotating in the direction of arrows shown. The arrows don't really matter. It could have been clockwise as well. It doesn't matter. So first we need to realize that the weight of the sphere is going to be mg. And then let's make the components of tension. So tension's first component according to the rope will be in this direction, which will be t cos of theta. And then we'll have one component because of the tension in the upward direction. And of course, I'm just dismantling this component of tension, right? So this becomes t sine theta. Now notice that what forces are equal to what components. If I replace this t sine theta over here, then there is no problem. So this is going to be t sine theta. And we have the central component over here that is pointing towards the center as well. So I can see that the weight is being supported by t sine theta component, right? So mg will be equal to t sine theta. This is my equation number 1. Equation number 2 will come from the idea that this central component is responsible for the circular motion, for providing the necessary centripetal force. So the second idea comes from that the centripetal force is being provided by the tensions cos theta component. So what's the formula of centripetal force? That is mv square over r equals to t cos theta. It could have been mr omega square equals to t cos theta. Depends on what formula you want to use out of mv square over r or mr omega square. You will generally find that v square over r is the one that you use mostly, but we understand that it could have been mr omega square as well. It does not matter. Okay. So these are the two equations. This is equation number 2. These are the two equations which are used to solve this system. You generally start from this. This helps you find out the value of tension because weight is given to you, the angle is given to you, so you find tension. When you find tension, you go to the second step and you find out the value of centripetal force and consequently probably the value of velocity or the value of the radius of the circle. And of course, radius of the circle will be this one. This is the radius of the circle that the object will rotate in. Okay, this is one of the common cases. The next one is the water bucket problem, and you will see that I've solved a question in the recent past papers in 2021. You will see that this is a problem that exists. This is a problem that if you didn't know, you might not be able to solve the question altogether. So let's see what this problem is. So you might have seen that in some physics videos, they have a bucket of water and the person standing at the center tries to rotate the bucket of water and shows you that the water in the bucket does not fall on its head when there is a rotation, right? And this also goes for those, let's say for playground, you can say swings or playground toys in which you see that the roller coasters or playground objects or a playing material for the children does not fall down from a curved track or from a circular track. What's the physics behind it? What's actually happening? So before starting with this, we need to realize that the centripetal force comes due to the resultant of many forces. So the first thing that we need to keep in our mind is that the centripetal force is provided by a combination of other forces or other than centripetal force. So the formula is going to be F equals to ma. This side deals with the centripetal force and this side deals with the forces that will provide the centripetal force. Okay, so it's going to be a result of the forces. So first we need to identify, let's say this is the top situation, right? So what's happening at this point? If this is the center of the circle and it is connected by a rope that has a tension T, then tension will be at the center of the circle. It should be towards the center of the circle, because if there is no tension, then there will be no circular motion. It won't be able to rotate. Second, we understand that the weight of the object, mg, will also be towards the center of the circle, right? Now, because of these two forces, there will be a centripetal force, right, as a resultant of them. So the resultant of these two forces gets equated as tension plus mg, because they're both helping or they're both acting in the same direction, equals to mv square over r. Let this distance be r, and let's say this is the tangential velocity v, and let's say this is the curved speed or the angular speed omega, right, which is of course equal to mr omega square as well, whichever you want to use. Now, since weight is already known, we understand their masses, we understand the velocity, we have almost all the variables. We don't have the variable for tension generally in the questions. He can ask you about the speed as well, but tension is what he's going to ask you generally. So since tension is supposed to be found out, we take mg over there. This becomes T equals to mv square over r minus mg, right? So this will be the formula when the system is at the top. Now notice that if you were dealing with all these forces in terms of accelerations, right? So T divided by m would be equal to v square over r minus g. So what is the value for g? G is equal to 9.81 minus the centripetal acceleration AC, which is tension per mass, right? So generally in these circumstances, we realize that if we need to make sure that the water does not fall down, then the centripetal acceleration needs to be greater than 9.81. And if your speed is not high enough to make sure that your answer is greater than 9.81, then of course the remaining force has to come from tension, right? So that's the physics behind it. Okay, so moving on to the case where we are at the bottom. So what happens when you're at the bottom? The tension is still in the upwards direction because you need to make sure that the thread is connected and the circle completes and the rotation completes. But this time around, the weight is downwards. And centripetal force will be as a result of these two components acting, which will be F equals to mv squared over r. So in place of F, I'm going to write down the subtraction or the difference of both of them because they're acting in the separate directions. Plus, tension has to be greater than the weight, otherwise the rope will break down. If the weight is greater than the tension, then the system fails to exist, right? So that's why I'm writing down T minus mg equals to mv square over r. Now since T is required, so T is equal to mg taken over there becomes mv square over r plus mg. Okay, all right. So under these circumstances, we can see that tension at the bottom and tension at the top comes out as, this will be mv square divided by minus mg, and this is mv square over r plus mg. You can notice that at the bottom, since they are being added together, the force of tension required to do the job is much greater. And at the top, the force of tension, since it is being subtracted from this value, it will be much smaller, or it will be smaller than the bottom force. So generally, tension at the bottom is greater or sometimes much greater than the tension at the top, right? Primarily because of mathematics. And plus, if you take a bottle of water, if you take a bucket of water and you try to rotate this, you will realize that when you come to the lower end during that demonstration, you will feel that your arms have to do a lot of work. The arms feel a lot of stress and strain while they're doing this, as opposed to when the arm is at the top. Even if you don't take a bucket of water, if you don't take a glass of water, so anything like that, just rotate your arm by standing, let's say, over here, and rotate your arm over your head as quickly as possible. You will see that the highest force or the highest strain you feel on your body is when the arm is crossing your legs and when it is at the lowest point. And this is the reason why, right? Because not only did the weight, but the tension has to support, or the tension in your muscles have to support or provide the centripetal acceleration for that job as well. But don't do it too much, it may strain your arms as well. This is just for a demonstration purposes. Now we'll move towards the questions that involve this idea, the water bucket problem, and involves these equations. If you hadn't done this before, you might not be able to understand what those equations actually mean. But that's why I've conducted this lesson. So I hope that it helps you. This is what is meant by centripetal acceleration. So the acceleration being perpendicular to the velocity is the centripetal acceleration. Concern the marking scheme to memorize the answer. All right. So the mass is given, the diameter is given. And of course, first the car exists at this point, then the car may exist, or at some point later in life will exist at this point. Okay. And then of course, come down to continue its journey towards that side. We understand this, okay? So the mass is given, everything is given. He says, state what happens to the magnitude of centripetal acceleration of the car as it moves around the loop from X to Y. So it decreases. And why this is happening, we will get to that later. So then he's explained why, if the car remains in contact with the track, why the centripetal acceleration of the car at point Y must be greater than 9.81 at least. So the reason is that the centripetal force is actually the resultant of the normal reaction and the weight at any time or at any point in time. Okay, so the centripetal acceleration has to at least minimum compensate the weight of the trolley, which acceleration is mg, of course, right? It needs to compensate for that at least, so that there can be some normal reaction, some contact maintained with the ground with the force. Okay. So centripetal force needs to be greater than the normal reaction, hence centripetal or centripetal acceleration should be greater than 9.8 at least. Let's go a bit deeper in each of these cases so that we can understand what we are discussing it in terms of theory. You see, first we need to establish that the centripetal force is the resultant of two cases. First we need to establish this. So the resultant force Fr equals to ma. This is a centripetal force and this is the resultant force. In our situation, let that be in any case, weight is being, or the resultant is being found by using weight and normal reaction, sometimes plus, sometimes negative. We'll get to that later. Okay. And then we have mass into acceleration. So ma. Now let's look at it in terms of the circular motion. So when it is at point x, the weight is downwards, the normal reaction is upwards, and in this case, most definitely, both are actually in the opposite direction, right? So normal reaction at the bottom, at this case, normal reaction should be greater than the weight. Only then the resultant will be in this direction, causing centripetal acceleration, right? So this will be nr minus w equals to mv square over r. Okay. So the normal reaction actually becomes equal to not only the centripetal force, which is mv square over r, plus also the weight. So at the lower point, the normal reaction is going to be very high, or is going to be higher than the top point. So this is what happens at the bottom, at least. This is the bottom mechanics. Now let's go to the top. The weight is also downwards. The normal reaction from the surface is also downwards. They're both in the same direction. And the resultant is going to produce a centripetal acceleration. So since, according to F equals to ma, in this case, both are going to add it together. So W plus the normal reaction equals to mv square over r. Now, since we are interested to find the normal reaction, because this is what changes, weight remains the same, that is mg, and centripetal acceleration is because of the resultant. So let's make normal reaction the subject of the formula. So that becomes mv square over r minus the weight. So at top case, the normal reaction slightly reduces because the weight is being subtracted. And at the bottom case, it slightly increases because weight is being added into the system. Okay. So this is why we're getting these answers, that when it goes from x to y, when it goes to the top part, the whole answer is becoming smaller. So the centripetal acceleration will be smaller. Okay. All right. And the same answer can be, same idea can be used to explain this part too as well. Let's move to the next question. He says we need to show whether the car is in contact at point y or not. First, we need to find out the velocity at point y. What will be the velocity at point y? So the height change from this point to this point is actually 62 centimeters, right? So if it has a certain velocity moving at this point, when it goes to this height, it will lose kinetic energy and convert this into gravitational potential. So there will be a fall in velocity. So we can use simple equation of motion, either use it in terms of energy, right? Energy calculations, or you can do this in terms of kinematics as well, that v square equals to u square plus 2 into negative 9.81 because it's moving against gravity, and then 62 into 10 raised to power minus 2 to convert this into meters, right? So this is our initial velocity, which was given to us as 3.8 square. So when you take the under root over the other side, and of course this is going to subtract from this value, so this comes out as 1.51 meters per second. So when the object is at the location y, it must be moving at 1.51 meters per second. Now let's go back to the equation at the top. What's happening at the top? You see, normal reaction, if he says that it maintains a contact, for example, that the car is in contact or not, normal reaction may become 0 or should be greater than 0, at least should be greater than 0. So let's rewrite the equation for the top part again. So when the trolley is at the top, the normal reaction is equal to the centripetal force minus the weight of the object. So let's say normal reaction equals to mv square over r minus mg. Now, generally speaking, this is what we're looking at, right? And this is what we have to calculate. And we understand that this whole system should be greater than 0. This is one way of justifying the answer, right? The other way is going to be in terms of acceleration, which he uses. But let's look at it from the perspective of forces, right? So I say that the normal reaction should be greater than 0 to maintain contact. But is that the case? We're going to check this whether that is the case or not by using the equation normal reaction is equal to or greater than equals to at least mv square over r minus mg. So we suspect it should be greater than 0. It needs to exist. उसकी कोई ना कोई वैल्यू होनी चाहिए तभी वो greater than 0 होगा. तो अब हम इन वैल्यूज को कैलकुलेट कर लेते हैं. So this is, let's calculate this whole scenario on the side. So nr being greater than what? So mg, that is 230 divided by 1000 divided by 9.81 into velocity square at y, which is 1.51 square divided by जो radius था इसका, that will be 0.31 at that part, right? Radius of the acceleration or the circular motion minus the weight, which is 230 divided by 1000, right? Divided by 9.81, right? Multiplied by 9.81. So when you're done with this, sorry, this will not be divided by 9.81. This is just divided by 1000. To convert this grams into kg. So this is mg. So this is mg. And this is mv square over r. Notice that it should be greater than 1 point. It should be greater than 0. So we find that this answer comes out as 1.669 newtons. This comes out as 2.563 newtons. And we said that normal reaction should be greater than 0. It should be greater than 0. Is it coming out greater than 0? So when you subtract this, this comes out as negative 0.894 newtons. This is not equal to 0. This is not greater than 0, which means that the normal reaction does not exist, which means that the trolley is not in contact. The trolley is not in contact. Otherwise, normal reaction would have been greater than 0, or it would have been participating at least in contact with the trolley. Now, another way to justify this same situation, same scenario, is in terms of gravitational acceleration. You see, the whole system actually became normal reaction plus weight equals to the centripetal force. This was happening at the top because they're in the same direction. And we want to find it for the normal reaction, right? So in normal case, we know that mg is equal to the normal reaction, which is mg as well. But for the sake of understanding, we're going to write this down as ma. So ma, resultant acceleration, okay, minus mg plus mg equals to mv square over r. Now we realize that mass is same, so it cancels out from the whole equation. So what we are left with is simple normal acceleration or centripetal acceleration. Sorry, the acceleration provided by the normal reaction plus the gravitational attraction equals to the centripetal attraction, centripetal acceleration, which is v square by r. Let's take this over there, and we realize that the centripetal or the acceleration, circular acceleration by normal reaction is equal to centripetal force or centripetal acceleration minus the gravitational attraction. So if we want this number to be at least 0 or greater than 0, right? We understand that this is supposed to be greater than 0. Then this equation is supposed to go something like this: v square over r minus g. So when that goes over there, this means that g is less than and v square over r, this should be greater than this. So our final answer should have been greater than 9.81 meters per second square. Let's calculate the centripetal acceleration. Is it greater than 9.81 or not? Let's verify this. So to verify this, we will use v square over r. This becomes 1.51 whole square divided by r, which is 0.31. When you finally calculate this, you realize that this is going to come out as 7.25. 7.25 meters per second square. What did we need? हमें क्या चाहिए था? हमें चाहिए था कि इसकी gravitational acceleration 9.81 से ज़्यादा होनी चाहिए थी, या 9.81 से सेंटीमीटर ज़्यादा होता, बट सेंटीमीटर तो 7.25 है. अगर ये कम है तो इसका मतलब है नॉर्मल रिएक्शन एग्जिस्ट नहीं करता. या आप ये सोच सकते हो कि 7.25 जो है वो जिम्मेदारी ले ली सेंट्रीपिटल फोर्स ने, बाकी का कौन शेयर लेगा ताकि ये 9.8 बने? तो बाकी का शेयर नॉर्मल रिएक्शन की जिम्मेदारी थी, जो कि हम उसको नहीं दे सके. तो जिससे प्रूफ ये हो गया, साबित ये हो गया कि नॉर्मल रिएक्शन एग्जिस्ट नहीं करता और ये चीज कांटेक्ट में नहीं है. ठीक है, तो हमने उसको फोर्सेस से भी बैलेंस करने की कोशिश की है और हमने उसको एक्सेलरेशन से भी देखने की कोशिश की है. व्हाटएवर मेथड सूट्स यू, आप उसको अडॉप्ट कर सकते हैं. सो मूविंग ऑन टू द नेक्स्ट पार्ट, सजेस्ट व्हाई बट विदाउट कैलकुलेशन वेदर सी would be applicable for 460 or not. देखिए, if we observe it from in terms of acceleration, mass तो पूरी equation में से कट हो जाता है, और अगर आप यहाँ पर भी in terms of mass ले भी लेते तो mass इधर भी है, mass इधर भी है, resultant effect तो आंसर तो यही आ जाना था दोबारा, ठीक है, क्योंकि मल्टीप्लिसिटी में ये भी बड़ा हो जाता, ये भी बड़ा हो जाता, बट क्योंकि लीनियर इक्वेशन है तो दोबारा इनके डिफरेंस का आंसर यही आना था. हालांकि ये भी आंसर बड़ा आता, ये भी बड़ा आता, लेकिन आंसर डिफरेंस का यही आ जाना था दोबारा. So there is no difference. In terms of acceleration, it's easy to visualize because we can see that mass is cancelling out. And in terms of forces, उसको थोड़ा सा explore करना पड़ता. So I hope that we understand this top and bottom case. Please be very careful. This question I've seen that is getting repeated again and again in past papers. Define gravitational field strength. We know this is force per unit mass, which is the value of G, which is Newton per kg, or as meters per second square. But since he's referring to as field strength, we will refer to this as this one. If it had said gravitational acceleration, then we would have referred to this unit. So an isolated planet in uniform sphere, radius this, mass this, may be considered to be a point mass, rotating at a period of 24.6 hours. At the equator, calculate the up to 3 significant figures, field strength. So the formula is very simple. The formula is G equals to Gm over R square. So simply replace the values as 6.67 into 10 raised to the power minus 11 into the mass of the object is given to you as 6.4 to the power 23, and divide this with R square, which is 3.39 into 10 raised to the power 6 meters whole square. Don't forget to take the square. This will come out as 3.7 to 6 meters per second square. This looks like Mars. Yeah. So this is going to be 3.73. He said 3 significant figures, so we have to oblige. The centripetal acceleration, which is going to be A equals to V square over R, or it could have been omega square R as this one. Since we don't have the centripetal, since we don't have the tangential velocity, and we do have the time period mentioned, so I believe that we are going to use R omega square. So this is going to be simply 3.39 into 10 raised to the power 6, the radius, into 2 pi divided by 24.6 hours multiplied by 60 minutes multiplied by 60 seconds. And this has to be squared. Don't forget the square. So this is going to come out as 0.0171 radians per second, which is going to be 0.0171 up to, basically this was 706, which became 171. The force per unit mass exerted on the planet by the surface of the planet. This is an interesting question. You see, in terms of the surface of the planet, the normal reaction is in the upward direction and the force of gravity is in the downward direction, right? And this is the normal reaction. Now, the centripetal force is exerted because of the resultant of the two forces, right? So force of gravity, which is weight minus the normal reaction, which is in the upward direction, is going to cause the centripetal force. So let's replace them with the respective formula. So I understand that this is going to be mg as weight minus the normal reaction, which is generally equal to mg, but since centripetal force, since they are being rotated, centripetal force is involved. So some of the force is also the responsibility of centripetal force, right? So let's call this as ma, acceleration due to the normal reaction because of this direction of force. Okay, all right. Equals to centripetal force, which is mv square over r, which you just calculated in the previous part. Now we can see that the mass gets cancelled out from the whole equation. What we are left with is simple 9.81 minus, sorry, not 9.81, but the gravitational field strength of this planet was 3.73. So 3.73. And since we're supposed to find out the force per unit mass on the surface of the planet, so we're going to take the normal reaction onto this side and bring this over this side. What has the planet, or what does the planet have to provide in order to compensate or to act against the weight while the centripetal force exists? So let's bring centripetal force over here. So the answer of this v square over r was already found as 0.0171. So this, while coming on this side, will become negative. So 0.07171 equals to the centripetal acceleration, or at least force per unit mass due to the normal reaction. So when you subtract this, this comes out as 3.71. This comes out 3.71. So this is what's actually happening. The resultant of the gravity and normal reaction produce the centripetal force. Okay. All right. So because the Earth is moving, right, the normal reaction